change the frequency of the input signal, and we have to study or we have to note the what is the output response of the system. So in the steady state, the sinusoidal inputs to a linear system generates a sinusoidal response of the same frequency. So even though these responses are of the same frequency as the input, they differ in amplitude and phase angle from the input. So these differences are the function of frequency. So the sinusoids, it can be represented as complex numbers called phasors. Right? We know phasors. The magnitude of the complex number is the amplitude of the sinusoid, and the angle of the complex number is the phase angle of the sinusoid. Right? We know this. The magnitude of the complex number is the amplitude of the sinusoid, and the angle of the complex number is the phase angle of the sinusoid. So we can write this one, this complex number, this m1 cos omega t plus phi, it can be represented as in this phasor form, or you can say this polar form. M1 is the magnitude, and this phi 1 is this angle of the this complex number, and this omega is the frequency. The system causes both the amplitude and phase angle of the input to be changed. So therefore, the system itself can be represented by a complex number. Thus, the product of the input phasor and the system function yields the phasor representation of the output. So you can see this here. This is our input, right, with this magnitude m1 and this phase angle phi 1. And this is our system, the magnitude of m of omega and this angle of phi of omega. So now the output will be this one, right? So assume that the system is represented by the complex number m of omega and angle phi of omega. So the output is found by multiplying the complex number representation of the input by the complex number representation of the system. Similarly, the magnitude will be multiplied here. M0 will be, or the output magnitude will be mi, the input, the magnitude of the input signal, and m is the magnitude of our system. Similarly, the angle will be added, right? If it is multiplied, then it will be, angle will be added. So phi 0 is this phi I plus this phi. This will be our output. Same thing. So mainly we will discuss these plots. Okay, not this Nicholas chart, not this one. I forgot to delete it. So mainly we are going to discuss this Bode plot, polar plot, and Nyquist plot. Okay, mainly in these three things, or these three plots, we are going to study the frequency response analysis, or frequency, how the system behaves when we give the input as our frequency. So let's first see what is the Bode plot. Okay, so the main advantage of using the Bode diagram or the Bode plot. So the multiplication of magnitudes can be converted into addition. So furthermore, a simple method for sketching an approximate log magnitude curve is available. I will explain this while doing this Bode plot. Okay, so it is based on asymptotic approximations. Just like in our root locus, we are drawing the asymptote first, but in this case, this Bode plot, it is based on the asymptotic approximation. We don't have to do the exact curve. Okay, by drawing these asymptotes, we can approximate the system stability. Such approximation by straight line asymptotes is sufficient if only rough information on the frequency response characteristics is needed. Okay. The expanding the low frequency range by the use of a logarithmic scale for the frequency is highly advantageous, because you are going to use the logarithmic scale in this Bode diagram. So since characteristics at low frequencies are most important practical system, so although it is not possible to plot the curve right down to zero frequency, because this log 0 will be minus infinite, so we don't have to write down this curve to zero frequency. So although this will be not very much problem that we are not starting from the zero frequency. So let's see, details is given here. Details. Okay, so I will go slow here because this is very important, the Bode plot. So the basic of any frequency response is to plot this magnitude m and this phase angle I against input frequency omega, right? So in this plot, we have to plot two plots. First one is the magnitude and the angle. So, and then it will be plotted against the frequency, the input frequency. So when omega is varied from 0 to infinite, there is a wide range of variation in the magnitude and the angle phi. So and hence it becomes difficult to accommodate all such variation with a linear scale. Right, our frequency can be up to 10,000 radian per second. But so it will be very difficult to accommodate all such variation with the linear scale. So hence this H.W. Bode, he suggested the method in which the logarithmic values of the magnitude are to be plotted against the logarithmic value of frequencies, right? Without taking directly this frequency, we can plot this against this logarithmic value of frequencies. So such plots are called this logarithmic plots, which allow us to show wide range of variation in the magnitude on a single paper. So these two plots, the Bode plot is consist of two plots. First one is this magnitude expressed in this logarithmic values against the logarithmic value of frequency. It is called the magnitude plot. Similarly, the phase angle in degrees against the logarithmic value of frequency is called as the phase angle plot. So basically, we are going to do two plots. First one is the magnitude plot, and in another one the phase angle plot. Let's see what is this magnitude plot. The magnitude, it can be expressed in its logarithmic values by finding out the value of this 20 log g of j omega. Okay, so which is a unit of decibel denoted by dB. Because we have taken this 20 log, we are getting this dB. Unit will be denoted as in decibel and is dB. So such decibel values are to be plotted against this log base 10 of omega, because we are varying the frequency here, right? And we know S equal to the sigma plus minus this j omega. So as we are doing the frequency response, we will be only considering this j omega part. Okay, frequency response. So similarly, we can do this one. Right? In y-axis, we will have this magnitude in dB, and similarly in the x-axis, it will be log of omega. Similarly, in the phase angle part, it will be the angle of this g of j omega, and the x-axis it will be log omega. So note this one, this is important. To predict the closed loop stability from the frequency response of open loop system, the magnitude and phase angle of the open loop transfer function g of j omega and h of j omega is to be plotted against this log omega, not only this, only g of j omega. We have to consider the open loop transfer function, not the system transfer function, right? If you want to predict the closed loop stability. I think all of you know about this logarithmic scale or the semi-log papers. So to sketch the magnitude in dB and phase angle in degree against this log omega, the logarithmic scale is used. Okay, so this is available on the semi-log graph paper. So in such paper, the x-axis is divided into a logarithmic scale, which is non-linear one. Right? We know it will be a non-linear one. I think all of you have seen this semi-log paper, right? In this x-axis, we will have to take a non-linear value. And the y-axis is divided into linear scale. So hence it is called the semi-log paper, because the x-axis is divided into logarithmic scale and the y-axis is divided into a linear scale. So it is called a semi-log paper. In the x-axis, about the interesting part about x-axis is the distance between the 1 and 2 is greater than the distance between 2 and 3 and so on, right? I think you know about the similar paper, that it will be, if you take this one, then it will be 10, and then the next 10 will be 100, 1000, right? Then 10,000. So the distance between 1 and 2 is greater than the distance between 2 and 3, and so on. Similarly, on such scale, the distance between 1 and 10 is equal to the distance between 10 and 100, or between 100 and 1000, so on. So this distance is called 1 decade. And this distance is called 1 decade. That is 1 to 10, 10 to 100, and 100 to 1000, so on. And this distance is known as 1 decade. So this is because this log 1 equal to 0 and log 10 equal to 1. The distance is 1 decade, which is divided into 10 parts according to logarithmic scale. So let's not go to this one. There's many details of this similar paper. So it is necessary to find the logarithmic value of omega while plotting on x-axis, but the logarithmic scale available takes care of the logarithmic value of omega. We will see this while drawing the Bode plot. So the advantage of the scale is wide range of frequencies can be accommodated on a single paper. So as this log 0 equal to minus infinite, so it is obvious that x cannot be calibrated from 0. But as per the requirement, the smallest frequency may be selected as starting frequency, like our 0.01 and 01, etc. So this will hardly affect the result of our frequency response. So in simulograph paper, we cannot start with this 0 frequency. We can take the smallest frequency as per our requirement. So the y-axis is divided into linear scale. So let's see the standard form of a open loop transfer function, right? So it is given in the pole 0 form. So k dash the system gain, then s to the power z and s to the power p, then s plus z1, s plus z2, then in the denominator it is s plus p1, s plus p2 up to the number of poles and 0. So remember this, that either this s to the power z or s to the power p will be present at a time, not both, right? Because suppose this z is 2 and this p is 3. At that time it will cancel out, right? S square and s to the power cube, it will cancel out. So there will be only single s in the denominator. So either s to the power z or s to the power p will be present at a time and not both. But this form is not useful to sketch the Bode plot. So the Bode plot is drawn for this time constant form, okay? Because we have to identify the frequencies. And the time constant, or you can say the frequency is 1 by the time constant. So we have to convert our this open loop transfer function into a time constant form if it is given in the pole 0 form. Clear? Remember, the Bode plot will be drawn only after converting the pole 0 form into the time constant form. Similarly, you can calculate this k with respect to this k dash. So now our this g of s and h of s will be equal to this one in time constant form, k into 1 plus t1s into 1 plus t2s divided by s to the power p into 1 plus tas plus 1 plus tbs. This k is our resultant system gain and p is the type of the system, and all these t1, t2, ta, tb are the time constant of this 0 and poles. So let's go to this Bode diagram. Okay. So first let's see this one, the basic factor of a transfer function, right? So we know in our transfer function we will have a system gain k, an integral or derivative factor, right? We can this j omega is s, okay? So s to the power plus or minus 1. So if it is s to the power plus 1, then it will be a this derivative factor, and if it is 1 by s, then it will be integral factor. 1 by s means pole at the origin, and s means pole 0 at the origin. So if there is a pole at the origin, it will be a integral factor, and 0 at the origin, it will be a derivative factor. Similarly, the first order factor, right, like this one, 3s plus 1, we can write like this one. The value of s will be equal to j omega, and this t we have to write in the time constant form, and plus 1. So it may be either in the denominator or the numerator. Like in this case, the 3s plus 1, it is in the numerator, and this s plus 1 in the denominator. So in this case, the 3s plus 1, the time constant is 3 here. And similarly, in this equation, the time constant is 1. Similarly, the next one is the quadratic factor. It may be in the denominator or it may be in the numerator. But in this case, in the denominator, right? S square plus 5s plus 2. So we'll see that how our transfer function will behave if we have these terms. So let's first see with this gain, the system gain K. The log magnitude curve for the constant gain K is a horizontal straight line at the magnitude of this 20 log K decibel, right? Because in our the magnitude will be plotted in decibel. So we have to do this 20 log of K. So it will depend on the value of K. What is the value of K? So similarly, the phase angle of the gain K is 0, right? Because tan inverse of this imaginary by this real part. So imaginary is 0 by K. So the phase angle will be 0. The effect of varying the gain K in the transfer function is that it raises or lowers the log magnitude of the transfer function, right? We know if we vary the system gain K, our this overshoot can, or we can say the speed of the response can change. It may increase or decrease. So similarly, in this case, in frequency response, if we vary the system gain K, then it can raise or lower the log magnitude curve of the transfer function by the corresponding constant amount. But it has no effect on the phase curve, right? Because the phase angle of this K is 0. So it will not have any effect on the phase curve. So right, it will be a straight line. As you know, the log magnitude curve, it will be a horizontal straight line with this magnitude of 20 log K decibel. So if we plot this in the Bode plot, so we have taken the value of K equal to 5. Then the 20 log K will be this 14 dB. So it will be a horizontal straight line at the 14 dB. It will not depend on the frequency. It will always remain same. The value will be constant because this K is a constant value. Similarly, the angle will be right for K equal to 5. So the phi is tan inverse of this imaginary part by the real part. So in this case, we can say this, it is 5 plus j 0. So the imaginary part is 0 and the real part is 5. So the angle will be 0. So we can draw a straight line like this one for this angle, for this gain. So let's go to this integral and derivative factor. So let's see this as this derivative factor. Okay. So this g of s equal to s only. That means the derivative factor means 0 at the origin. So let's say our transfer function is only s. So in frequency response, we have to put the value of s equal to j omega, because we have to vary this value of omega. Okay. So this magnitude will be this magnitude of g of j omega will be 20 log of omega, right? Or we can say 20 log of this root over omega square plus 0 square. So we will get the magnitude will be 20 log of omega. So now in frequency response, we have to vary this value of omega. So if we put the value of omega equal to 0, then we will get minus infinite. So we are starting from this value of omega 0.1. So if we put the value of omega equal to 0.1, then we will get the value minus 20 dB. The magnitude value will be minus 20 dB. Similarly, for 0.2, it is minus 14 dB. So up to 1, when this omega equal to 1, then we are getting the magnitude to be 0 dB. Here you can see for 0.1 to this up to 1. So for 0.1, the magnitude is minus 20 dB. And when the omega equal to 1, you can see the magnitude is 0 dB. So we can say for a decade, right? Decade means the 0.1 to 1, or we can say 1 to 10. So for a decade, so in this case you can see 0.1 to 1, a decade. So we are seeing a minus 20 dB change. 0.1, it was minus 20 dB. And when the value of omega equal to 1, we are getting 0 dB. So for a decade, we are seeing a minus 20 dB reduction. So we can say this slope is a plus 20 dB. You can say we are adding a plus 20 dB, right? So minus 20 plus 20 will be 0. So we can say for a decade, there is a change in this 20, 0.1 to 1, there is a change in this 20 dB. So the slope, if we draw this line, then the slope will be this 20 dB per decade, right? So I will show you in the graph. So similarly, octave, we can see from this 0.1 to 0.2, it is 6 B by octave. So similarly, the phase angle will be tan inverse of this imaginary part by real part. So in this case, the real part is 0. So omega by 0. So we will get the angle, phase angle 90 degree. Or we are getting this magnitude plot to be the slope of 20 dB per decade and the phase angle to be 90 degree. So if we draw this graph for this magnitude plot, okay. So for 0.1, right, we have started our frequency at 0.1 and we have taken up to 1. 0.1 to 1. So this is 1 decade. Okay, this is 1 decade. So when our omega value is 0.1, it was minus 20, and omega value is 1, the value is 0. So this is our minus 20 and this is 0. So you can see it started from this 0.1 and it becomes 0 when this omega equal to 1, right? Because in this x-axis we are taking this omega value. So you can see this will be a linear line with the slope of this 20 dB per decade, right? So we conclude that, so if we have a 0, then the slope will be 20 dB per decade. And the angle is 90 degree. Okay, so angle is not that necessary. It is very easy to plot the angle. We have to focus on the plotting of this magnitude plot. Similarly, earlier it was a derivative factor, right? Only s. So if we take the integral factor, that is 1 by s. At 1 by s, so it will be this one. So when expressing decibel, the reciprocal of a number differs from its value only in sign. So that is for the number n, if 20 log n, it can be written as minus 20 log 1 by n, right? So similarly, for integral factor, the slope of the magnitude will be same but with opposite sign, right? For this pole at the 0 at origin, the slope was 20 dB per decade. Similarly, if there is a pole at the origin, only the sign will change. So it will be minus 20 dB per decade. And similarly, for octave, it will be 6 dB per octave. So this will be this minus 20 log omega, right? But in case of this one, we are getting only 20 log omega. But when there is a pole at the origin, we are getting minus 20 log omega. Similarly, the angle will be also minus 90 degree. So we can draw, right, from plus to this 0 up to this 0, we can see this is a 1. So from plus 22, it is going to 0 in a decade, right? From 0.1 to 1, it is 1 decade. So from plus 22, it is going 0. So we can say our slope is minus 20 dB per decade. So for a pole, our slope will be minus 20 dB per decade, and for 0, it will be plus 20 dB per decade. So let's see this first order factor. Okay, so this is a j omega t plus 1. That means this is a 0, right? It is the form of a 0. So similarly, in this case, we have to find the magnitude and the phase angle. The magnitude will be 20 log of root over of 1 square plus omega square into t square, right? So the magnitude 20 log of root over of 1 plus omega square t square. So for low frequency, that means if omega is much more less than this 1 by t, or we can see if omega t is much more less than 1, right? If 1 is greater than this term, very much greater than this term, then we can neglect this term and we will have only this magnitude plot to be 20 log of 1, which will be equal to 0. So for low frequency, this magnitude will be 0. And for high frequency, if omega t is much more greater than the value of 1, at that time we will get this magnitude to be 20 log omega t. Similarly, angle, it will be this tan inverse of omega t divided by 1, because the real part is 1 here, right? So omega t divided by 1. So for different value of omega equal to 0, we will get the angle to be 0. Omega equal to 1 by t, we will get 45 degree, and omega infinite, we are getting 90 degree. So it is a pole 0, right? So for 0, our slope will be this plus 20 dB per decade, or we can say plus 6 dB per octave. Phase angle plot, so we will ignore this one. So similarly, if it is a 0, okay, sorry, non-zero pole, it is a non-zero pole, then at that time we will get this magnitude to be minus 20 log root over of 1 plus omega square t square. Similarly, for low frequency we will get 0, and for high frequency this magnitude will be minus 20 log omega t. So the slope will be, you can see the slope is here minus 20, right? So it will be minus 20 per decade. Similarly, the angle will change, 0, minus 45 and minus 90. So we can see here for this transfer function, we will get the slope to be minus 20 per decade. So this is basic of this Bode plot. Then we will go to the plotting. Okay, this Bode plot is very easy, so do not confuse with anyone. So the main point is we have to find the initial slope of the Bode plot and the starting of the Bode plot in the semi-log graph paper, right? Because in this case, in this diagram, in this magnitude plot, we don't know from which point this magnitude plot will start. So we have to find this point, that at which point it will start. We know for pole it will be minus 20 per decade, and for 0 it will be plus 20 per decade. But we have to find out this starting point. So let's see this initial slope of the Bode plot. So let us say we have our open loop transfer function, this g of s and h of s equal to k divided by s to the power n. So for frequency response analysis, we have to put the value of s equal to j omega. So by putting omega into h of j omega is equal to k by j omega to the power n. So to plot the magnitude plot, we have to take this 20 log. So we will get the 20 log magnitude of k by this j of j omega to the power n, and we will get 20 log k minus 20 n log omega. Clear? I think this is clear. No need to explain this one. So the division will be in log magnitude will be this minus, and this multiplication will be this positive symbol. Okay. So 20 log k minus this to the power n will be multiplied here. So 20 into n log omega. So let's see for different type of system what will be the initial slope. Remember this equation, okay? This will be very much useful to find the initial slope and the starting point. So let's say we have this type 0 system where this to the power n is 0, right? So n is 0, so type 0 system. So this equation at this magnitude, it will become, if we put the value of n equal to 0, we will have left only this term, this 20 log k. Right, this will be the 20 log k only. If this n is equal to 0, the magnitude will be 20 log k only. So 20 log k, it will be a straight line because this k is a constant term. So it will not be affected by the frequency, change in frequency. So we will get a this like this a constant, this horizontal straight line. So this will be 20 log k. So let's see for this type 1 system. Type 1 means we have to put the value of n is equal to 1, right? So the magnitude is this 20 log k minus 20 log omega. So we have to find the intersection with the 0 dB axis, right? This is 0 dB axis. So at which point it will intersect, right? Because this is there is a pole at the origin, means there will be a minus 20 dB per decade slope. So that means it will intersect the 0 dB axis at some point. So intersection of 0 dB means the magnitude is 0, right? This is the magnitude. So the magnitude is 0. So 20 log k minus 20 log omega, right? Because the value of n is equal to 1. So by solving, we will get the value of k is equal to omega. For type 1 system, the value of k is equal to omega. At that time, our this magnitude plot will intersect the 0 dB axis. Clear this one? When the value of k is equal to omega, at that time the magnitude plot will intersect the 0 dB axis. So now we have to, while plotting this one for type 1 system, we have to locate the omega equal to k on the 0 dB axis, and at this point we have to draw a line of this minus 20 dB per decade till it intersects the y-axis. Okay, so we'll see in the example. Similarly, for type 2 system, we have to put the value of n is equal to 2, right? The magnitude of this one, this g of j omega and h of j omega is equal to 20 log k minus 20 into 2 log of omega. So it will intersect the 0 dB axis, means this value will become 0. This magnitude value will become 0 when this 20 log k minus 40 log omega are equal. So 20 log k equal to 40 log omega. So from this equation, we can see the omega square is equal to k. Right, the omega square is equal to k. So omega, the value of omega is equal to root over of k. So value of omega equal to root over of k. So hence the graph will intersect the 0 dB axis at omega equal to root over of k. So we have to locate the value of omega, which is root over of k, on the 0 dB axis, and we have to draw a line of minus 40 dB per decade till it intersect the y-axis. Okay, this initial slope clear? I think after doing some example, it will be very much clear. Okay, so let's see for this diagram. Okay, for a type 1 system. So for type 1 system, this is your 0 dB axis. Okay, this is your 0 dB axis. So the 0 dB axis and the magnitude plot, this is your magnitude plot. It will intersect the 0 dB axis when this value of omega is equal to k. So to draw the slope or to draw this point, right? Because we don't know this point, the starting of our asymptote, we don't know this point. So how can we draw this minus 20 per decade line? So for a first order system, first we have to locate the value of omega, which is equal to k. So suppose k is given 10. So we have to find the value of omega equal to 10. So from this point 10, we have to draw a slope of this minus 20 dB until it intersects this y-axis. So now this point will be our starting point of the magnitude plot. Similarly, for the second order system, we have to find this omega equal to root over of k. So suppose k is 9. Okay, the gain value is given 9. So omega is equal to 3. So in the x-axis, we have to find the 3 value, and from that we have to draw this minus 40 dB per decade line until it intersects this y-axis. Clear? Minus for a single pole it will be minus 20 dB per decade, and for double pole it will be minus 40, and for triple pole it will be minus 60 dB per decade. So the same apply for the 0 also. So it is given here. So if we have a third order type 3 system, then the value of omega will be equal to this k by the k to the power 1 by 3. So at that point our this asymptote will intersect the 0 dB axis. So we'll see, I will go through this later. So first let's see an example. Okay, so let's quickly go through the steps how to plot the Bode plot. So first we have to identify the corner frequencies. Okay, so I will see that. So and draw the asymptotic magnitude plot. The slope will change at each corner frequency by this plus 20 dB per decade for 0 and minus 20 dB per decade for pole. And for complex conjugate pole and 0, the slope will change by this minus plus 40 dB per decade, right? Complex conjugate means there are 2 pole and 2 0. So it will be this 40 dB per decade. If there is single pole, it will be minus 20 dB per decade. If it is a complex conjugate or double pole, it will be this minus 40 dB per decade. So for type 0 system, draw a line up to the first corner frequency having a 0 dB per decade slope. Right? For type 0 system, we have to draw a line up to the first or the lowest corner frequency having a 0 dB per decade slope. Similarly, for type 1 system, we have to draw a line having this minus 20 dB per decade up to omega is equal to k, up to the lowest or the first corner frequency. Similarly, for type 2 system, we have to draw a slope of this minus 40 dB per decade up to omega equal to root over of k. So then draw a line up to second corner frequency by adding the slope of the next polar 0 to the previous slope and so on. And the next step is to calculate the phase angle for different value of omega. So we'll go through this later. So let's go through this simple example how to draw the Bode plot. So this is our unity feedback system, this G of S, H of S. So the sketch the Bode plot for the transfer function. So this G of S, H of S is equal to 1000 divided by 1 plus 0.1 S into 1 plus 0.001 S. So this transfer function is already in the time constant form. Okay, so we don't have to convert it into the time constant form. It is already in the time constant form, right? Because this 0.1 is our time constant, and here also this 0.001 is also the time constant. So first we have to draw. Okay, so let's ignore this, determine this PM, GM, and this stability. So let's first how to draw the Bode plot for a given open loop transfer function. So the first step is to put S equal to J omega. Okay, we have to put the value of S equal to J omega. So now this G of J omega is equal to 1000 divided by 1 plus J into 0.1 omega into 1 plus J into 001 omega. Clear? We have replaced S with J omega. So we can see this is a type 0 system, right? Type 0 means the power of S is here 0, S to the power 0. So it is a type 0 system. So therefore, the initial slope of the Bode plot is 0 dB per decade. If it is a type 0 system, then the initial slope will be 0 dB per decade. And if it is a type 1 system, it will be minus 20 dB per decade. And if it is a type 2 system, then the initial slope will be minus 40 dB per decade. So then the starting point, we can calculate the starting point by is 20 log k, right? To the starting point. So it is varied for only this type 0 system. Okay. For type 1, type 2, do not determine the starting point by this formula. It is only varied for type 0 system. So 20 log k is equal to this one is 60 dB. So this is the starting point on our y-axis. So it is only for this type 0 system. So next, the corner frequencies. This corner frequencies are calculated by this time constant, this 0.1 and this 0.001. So the first corner frequency is, we know the frequency is 1 by this time constant. So 1 by 0.1. The first corner frequency is 10 radian per second. Similarly, the second one will be 1 by 0.001. So that will be 1000 radian per second. The omega 2 is 1000 radian per second. So we have only two time constants, so we have two corner frequencies. The corner frequency is defined as the frequency at which two asymptotes break. Okay, it is the corner frequency, the actual definition of the corner frequency. So we have two corner frequencies because we have two time constants. So one corner frequency is 1 by 0.1, which is 10 radian per second, and the another corner frequency is 1 by 0.001, which is equal to 1000 radian per second. So it is a type 0 system, right? So the starting point is calculated by 20 log k, which is 60 dB. So we have to mark the starting point 60 dB on the y-axis, and then draw a slope of 0 dB per decade up to the first corner frequency. The first corner frequency is, or the lowest one is the 10 radian per second. Okay, so up to this 10 radian per second, we have to draw a straight line, or we can say 0 dB per decade. So semi-log graph paper. So I'm just drawing this normally. Okay. So let's say we have taken the starting frequency is 0.1, and then this is 1, this is 10, similarly this is 100. Okay. So from this 0.1 to 1, it is 1 decade. This is 1 decade. Similarly 1 to 10, 1 decade, and 10 to 100, 1 decade. So our first step is to, it is a type 0 system. The starting point of our magnitude plot is 20 log k, which is we have got this 60 dB. Okay, so we are getting only positive, so I am taking only the positive. So let me take also the negative one. So let's say this is minus 20 dB, this is 0 dB, and this is this is 40, 60. Okay, this is 20, 40, and this is, let's say, 60 dB. So all these are in dB. Okay, and in the y-axis it is radian per second. So as it is our type 0 system, so we can find the starting point on the y-axis as 20 log k, and we got the starting point to be 60 dB. So the next point is to mark the starting point 60 dB on y-axis and draw a line of slope 0 dB per decade up to the first corner frequency. So what is the first corner frequency, or the lowest one? 10 radian per second. Okay. So 10 radian per second means this one. This is your 10 radian per second. So up to this we have to draw a 0 dB per decade slope. Straight line. Okay. 0 dB per decade up to this point. Up to this point. Okay. So then what is the next step? So from the first corner frequency to the second corner frequency, draw a line of slope, right? The earlier was 0 dB, then we have to add a minus 20 dB because this corner frequency belongs to the pole. So for a pole, it will be a minus 20 dB per decade. So 0 minus 20, so it will be minus 20 dB per decade. So this is the first corner frequency is 10, and the next one is the 1000. Okay, this is 1000. The next corner frequency is 1000. So up to the next corner frequency, we have to draw a minus 20 dB per decade line. Okay, so this will be our minus 20 dB per decade. Minus 20 per decade slope from the first corner frequency to the next corner frequency. Similarly, from the second corner frequency to the next corner frequency, if given, okay, जब next corner frequency अच्छी, ताहले नहले भी हमको ड्रॉ वी हैव टू ड्रॉ ए लाइन हैविंग ए स्लोप ऑफ earlier it was -20, so we have to add another -20, so it will be -40 dB per decade up to the next corner frequency. यदि नथिबो then we have to just left it, right, माने ड्रॉ करी के हमें छाड़ दब because we don't know the next corner frequency. So similarly this slope will be -40 dB per decade. This slope will be -40 dB per decade. So this will be the magnitude plot. Okay. So you can see here in this diagram also. So it is taken from 1, okay, but I have taken from the starting frequency from 0.1, but in this graph it is taken 1 because our next corner frequency is 10, so it is taken from 1. So we have identified the initial starting point of this asymptotic plot is 60 dB. Okay, this is our 0 dB line. This is our 0 dB line. 10, 20, 30, 40, 50, 60. So from this 60 to the next corner frequency, the next corner frequency is 10 radian per second. So it will be a 0 dB per decade line. And now this corner frequency omega 1, it belongs to the pole. For a single pole, so it will be -20 dB per decade. So we have to draw -20 dB per decade line here up to the next corner frequency. That is omega 2 is given as 1000, right? 1000. So from that 1000, we have to draw another -20. So that -20 will be added to the previous -20. So now the next slope will be -40 dB per decade. So from this next corner, the second corner frequency, we have to draw a -40 dB per decade slope up to the next corner frequency. If not given, then just we have to just leave it there. Okay, only after drawing the -40 dB per decade. Clear this this magnitude plot?
Yes, sir. Slope टा केमती पाउछन सर?
हां,
बस स्लोप टा केमती पाउछन ती माने
अच्छा स्लोप टा परे कभी केमती ड्रॉ करिबा, किंतु एटा केमती हबो क्लियर तो?
हां सर.
ओके,
सर सबु बेले हम इनिशियली 0 डी पर टेकन नो
ना ना जदी हमर टाइप 0 सिस्टम अछि, टाइप 0 थिबो ताहले
दीटा जेमिति दीटा पोल अछि दीटा कॉर्नर फ्रीक्वेंसी अछि ताले हमको 40 डी बाय डिकेड देखा पड़िबो.
हां लास्ट 40 डी जदी हम दीटा पोल अछि ना तो फाइनल स्लोप -40 डी पर डिकेड हबो. जो तीनटा था ना तीनटा पोल ताहले तो फाइनल स्लोप रहंदा -60 डी पर डिकेड.
तो सेटा देखा पड़िबो.
हां तो आसी एग्जांपल करिया बहुत गुडा अछि ला. तो बेसिक टा क्लियर केमती हमर एसिम्पटोट जो मैग्नीट्यूड प्लॉट हैला.
यस सर.
फेज एंगल प्लॉट टा बहुत इजी हैला, तो एथिरे तम बेसी मुंड करिया दरकार नहीं पड़ियाला. तो फेज एंगल प्लॉट हम बाहर करिवा फॉर डिफरेंट वैल्यू ऑफ ओमेगा. सो ए इक्वेशन पई कोन होबो हमरो tan इनवर्स ऑफ 0.1 ओमेगा, राइट. एंगल हम जानि छे एटा पोल अछि, सो माइनस tan इनवर्स द imaginary part by real part. So real part is 1 and the imaginary part is this 0.1 omega. So -tan inverse 0.1 omega. Similarly, I would pole by -tan inverse 0.001 omega, imaginary part by real part. So by taking different value of omega, we can find this angle, right? यहाँ पे कितने आसीबो this first pole by और second pole by angle कितने आसीबो, then we have to add the poles, right? Because दीटा हमारा pole अच्छी, तो the angle दीटा summation है जीवो. इट बेसिकली डिफिकल्ट नहीं एंगल कैलकुलेशन. सिंपली ए पॉइंट गुडा को नहीं कि हमें ड्रॉ करियो हमरा ग्राफ पेपर रे.
और आधा दे दियो मत मुंडा खराब नहीं कर ठीक है काट के दे दियो.
कौन को जी सो एंगल प्लॉट टा बेसी डिफिकल्ट नो हो. Just we have to take this tan inverse of this imaginary part by real part. यदि pole raise then minus हबो, 0 थिले plus हबो. Then we have to add all these angle of the pole are 0. So we can easily plot, right? For 50 radian per second, the angle is 81.5 0.46. For 100 radian per second, angle is minus 90. So you can easily plot that. For 50, right? For 50 it was 81, and for then 100 it is this 90. Something or ये प्लॉट करी पारे जेमते हमर ग्राफ प्लॉट हो क्लियर एटा किछि बेसी डिफिकल्ट नाही हमको मेनली हैला इंपोर्टेंट देवर अछि मैग्नीट्यूड प्लॉट रे सो लेट्स देखिए फास्ट ऑर्डर सिस्टम रे उठेला तो टाइप 0 थिला बोली हमें 20 log k करी की स्टार्टिंग पॉइंट बाहर करथिले 0 dB पर डिकेड करी के हमें लाइन ड्रा करथिले हैला सेटा ओनली फॉर 0 टाइप 0 सिस्टम so देखिए टाइप 1 सिस्टम देखिए हमें नेक्स्ट so first step is to we have to put s equal to j omega and we have to check whether it is in the pole 0 form or in time constant form यदि pole 0 form में कर दो ताहले तमरो भूले जो मैग्नीट्यूड प्लॉट काहे कि ना यदि तम pole 0 प्लॉट तमरो गेन वैल्यू अलग आसीयो हैला आ गेन वैल्यू डाउन डिपेंड करे स्टार्टिंग पे तो हमर ठीक s equal to origin रे अछि so we can neglect omega equal to 0 कहीं ना ओमेगा 0 रे log टा हो हमरा minus infinite so we have to ignore this pole okay pole at the origin so neglecting this we have two corner frequency one is 1 by 0.1 and 1 by 0.001 so 10 radian per second and 1000 radian per second so it is not the type 0 system okay so it is a very tricky one to identify the starting point of the this magnitude plot. So we have already discussed for type 1 system the initial slope will be minus 20 per decade. But for type 0 it was 0 dB per decade, right? But for type 1 it will be minus 20 per decade the initial slope. So so we have to mark so I am starting from frequency 1 okay 1 this is 10 this is 100 and this is 1000 so we have frequency up to corner frequency up to 1000 so first we have to find the initial point it is a type 1 system so we cannot take 20 log k okay so we have to find the starting point how so we have to mark on the omega axis where omega is equal to k okay so k value is 1000 so we have to mark that point this 1000 on the omega axis so 1000 is this one right this 1000 is this point on this omega axis which k equal to omega which is equal to 1000 so we have to mark this point on this x-axis, which is our 1000. So we know our initial slope will be this minus 20 per decade because we have a pole at the origin, or we can say we have a type 1 system. So now, as we mark this omega 1000 on the x-axis, from that point we have to draw the initial slope of 20 dB per decade. So from this point we have to draw 20 dB per decade line. So now this will be our starting point. Right? We cannot draw the starting point from the x-axis. We have to draw the starting point. We have to draw the starting point from the x-axis, but we cannot draw from this y-axis for type 1 to or higher than the type 1 system. Only for type 0 system we can find this starting point by doing 20 log k. But for type 1 system we have to identify the value of omega equal to k. So 1000. So from this point we have to draw this minus 20 dB per decade slope. Okay, minus 20 dB per decade slope. So it may intersect at any point. Okay, we don't care about this one, but we have to make sure that we are starting from the point where k equal to omega. So from this point we have to draw this minus 20 per decade slope. So it may intersect at 30, 40, 50. Okay, so we don't care about this one. So okay, so this is done. So now the next step is we have to see what are our corner frequencies. Okay, the first corner frequency is 10. So we have to mark 10 here at this point on this center 10. Clear? So now this corner frequency 10, it belongs to a pole, right? This corner frequency belongs to a pole. So our initial slope was 20 dB per decade, and then there is another pole. So it will be this minus 20 plus this minus 20. So it will be this minus 40 dB per decade. So it will be this minus 40 dB per decade. Okay. So up to the next corner frequency 1000. Just let me erase it. Okay. So this is our first corner frequency. So this is our 20 dB per decade slope. So now from this we have to draw a 40 dB per decade slope up to this 1000. 1000 is the corner frequency, the next corner frequency. So this slope is of minus 40 dB per decade. We have to write this, okay, the slopes. So up to the next corner frequency 1000. So 1000 also a corner frequency. So we have to start another asymptote from this corner frequency. So this corner frequency belongs to the pole. So we will have to add another minus 20 dB to this minus 40. So we will get a minus 60 dB per decade slope. Now this slope will be minus 60. Minus 60 dB per decade. So excuse me for my graph. Okay. So let's see here. The starting point we have to find for type 1 system is where this omega is equal to k. So k is 1000. So at 1000 we have to mark on this 0 dB axis. And from this we have to draw a slope of this minus 20 dB per decade. Okay. So next we have to see the corner frequency. The first corner frequency 10. So this is our 10. So this 10 belongs to this pole. So we have to add another minus 20. So now from this, the slope will be this minus 40 up to this 1000 radian per second. Right? This is 1000 radian per second. So we have to draw this minus 40 dB per decade line up to this minus 60 dB per decade. So next corner frequency, this one, this 10 to the power 3 or 1000. So it is also belongs to a pole. So we have to add another asymptote with minus 60 dB per decade because it also belongs to the pole. So the final slope will be minus 60 dB per decade because we have total 3 number of poles. So we will get the final slope will be minus 60 dB per decade. Is it clear? Na kichhi doubt achi?
So say minus 60 dB per decade ta outhar dige.
Our starting initial slope ta minus 20 achi na pole at origin.
Yes sir.
तो तापर आउ गोटे पोल अच्छी केते रे 10 कॉर्नर फ्रीक्वेंसी रे तो -20 आउ गोटे -20 मिसियो -40 हला तो आउ गोटे कॉर्नर फ्रीक्वेंसी 1000 रे तो से कॉर्नर फ्रीक्वेंसी टा पोल रो तो से पोल पई आउ गोटे -20 भी ऐड हबो हला ना बुझी पारलनी
सर बुझिल एसे 10 ने -20 अछि पुनी आउट -20 कर हला 10 पई सेमती 1000 रे -40 अछि पुनी -20 कर
आउट मा जेतरा पोल थिबो सेतरा माइनस कर कि -20 कर जियो हला तो सपोज एटी 0 थांता 1000 ओटी 0 थांता हला तो 0 पे हमर स्लोप टा केते +20 dB पर डिकेड तो सेत +20 dB ऐड करियो एते तो प्लस कले केते हिजिबो एटा -20 तो स्लोप टा हेंदा एमती -20 रे हेतांता हला ये तमर पोल अछि सेति में हमें -20 ऐड करले तो 0 थांता ताहेले हमें +20 ऐड करथांते पूरा एग्जांपल अछि करिबा तो जस्ट बी श्योर दैट यू अंडरस्टैंड दिस मैग्नीट्यूड प्लॉट ओके तो कार किछि डाउट अछि एथिरे ओटी पढी वाला काली हम डिस्कस करिया डिटेल्स रे बहुत गुडा एग्जांपल करिबा तापर तम डाउट क्लियर हो
सर गेन क्रॉसओवर फ्रीक्वेंसी टा जोटा 0 एक्सिस को जोटा 0 dB एक्सिस को जोटा क्रॉस करियो माने इंटरसेक्शन पॉइंट
जोटा 0 dB एक्सिस क्रॉस करिवो से जगह सेटा हो हमरो जो फ्रीक्वेंसी रे मैग्नीट्यूड प्लॉट 0 dB एक्सिस को क्रॉस करिवो सेटा हमरो गेन क्रॉसओवर फ्रीक्वेंसी सिमिलरली जो फेज प्लॉट टा जो फ्रीक्वेंसी रे -180 क्रॉस करिवो सेटा हो फेज क्रॉसओवर फ्रीक्वेंसी देखो ए केस रे एटाला मैग्नीट्यूड प्लॉट 0 dB को ए जगह ए फ्रीक्वेंसी रे ଆମର ଇଣ୍ଟରସେକ୍ଟ କରିଛି ହେଲା। ତ ଏଇ ଫ୍ରିକ୍ୱେନ୍ସିଟା ହେଲା ଗେନ୍ କ୍ରସ୍ ଓଭର ଫ୍ରିକ୍ୱେନ୍ସି। ତ ଏଇ ଫ୍ରିକ୍ୱେନ୍ସିଟା ହବ ଆମର କେତେ 1500 ପାଖାପାଖି ହବ ଆଉ ରଫଲି ଦେଖିବା ଯଦି 1500 ରେଡ଼ିଆନ୍ ପର୍ ସେକେଣ୍ଡ ରଫଲି କହୁଛି। କାଉଣ୍ଟ କରିବାକୁ ପଡ଼ିବ ବସିକି, ଏଇଟା ତ 1000 ଅଛି ନା, ତ 1500 କି 2000 ପାଖାପାଖି ହବ, ତ 2000 ପାଖାପାଖି ହବ ହେଲା। ସେଇଟା ହବ ଆମର ଗେନ୍ କ୍ରସ୍ ଓଭର ଫ୍ରିକ୍ୱେନ୍ସି। ସିମିଲାରଲି ଏଇ କେସ୍ରେ ଆମେ ଦେଖିପାରିବା ଏଇଟା ସପୋଜ୍ ଏଇ ପଏଣ୍ଟରେ -182 କ୍ରସ୍ କରୁଛି, ତାହେଲେ 10⁴ ଇଜ୍ ଦ ଫେଜ୍ କ୍ରସ୍ ଓଭର ଫ୍ରିକ୍ୱେନ୍ସି। ଯଦି ଏଇଟା ଇଣ୍ଟରସେକ୍ଟ କରୁଛି କିନ୍ତୁ କରୁନି ଏଇ କେସ୍ରେ, ଯଦି ଏମିତି ଇଣ୍ଟରସେକ୍ଟ କରୁଥାନ୍ତା ତାହେଲେ ଏଇ ପଏଣ୍ଟ ହେଲା ଆମର ଫେଜ୍ କ୍ରସ୍ ଓଭର ଫ୍ରିକ୍ୱେନ୍ସି। ପଢ଼ିବା ଡିଟେଲ୍ସ ହେଲା, ବହୁତ ଜିନିଷ ଅଛି। ଆଉ କାହାର କ'ଣ କିଛି ଡାଉଟ୍ ଅଛି ନା କାଲି ପଢ଼ିବା? ତ ଏଇଟା ମୁଁ ସେଣ୍ଡ କରିଦେଉଛି, ଜଷ୍ଟ କାଲି ଟିକେ ଓଭରଲୁକ୍ କରିଥାଏ ଏକ୍ଜାମ୍ପଲ୍ ଗୁଡ଼ା, କିନ୍ତୁ ଆମକୁ ବୁଝିବା ପାଇଁ ଇଜି ହେବ।